My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, I'm going to discuss features of the Central Processing Unit, or CPU, that are useful for supporting multiple applications sharing a computer system simultaneously. In particular, I'll introduce multiprogramming and discuss the hardware requirements to support multiprogramming. I'll discuss CPU privilege modes, x86 protection rings, mode switches, and briefly introduce interrupts. The first concept to introduce is multiprogramming. And multiprogramming is simply the idea that we can run multiple processes or multiple instances of potentially several programs at the same time. And we can do this by having the CPU switch quickly among the different processes, enabling all of them to make forward progress per unit of human perceivable time. The CPU will switch quickly enough to provide the illusion that all the processes are running at the same time, even if we only have one processor core. In the vast majority of modern computing systems, with the exception of some special purpose systems, are a multiprogramming system. Some of the old computer systems of the day were batch systems that only ran one application at a time. Now, in order to support multiprogramming, we have to have certain features of our computer hardware. First of these is an interrupt mechanism for enabling preemption of running processes whenever some kind of event occurs. We have to have a way of stopping a process, handling an event, and then restarting the process. We need to have a clock so that we know how long a process has been running, and we need to have CPU protection levels to restrict access to certain instructions to prevent processes from hijacking the system or just trying to bypass the operating system altogether. We also need to restrict access to memory in order to prevent reading and writing to memory that a particular process does not own, belongs to somebody else. 2 CPU protection levels are sufficient: a protected mode and a privileged mode. These modes are also called the supervisor mode or kernel mode and user mode. In kernel mode, all instructions on the CPU are enabled, and the kernel can access all memory on the system. In user mode, the CPU disables all the privileged instructions and restricts most direct memory operations. Thus, a user program must make a system call to the operating system to request memory or perform other resource allocation tasks. In this way, the user processes are effectively sandboxed both from the system and from each other. On the Intel-based systems, x86 and x86-64 systems, there are actually 4 modes available. These are implemented by what are known as x86 protection rings, which consist of 4 privilege levels numbered 0 through 3. Ring 0 has the greatest number of privileges. Code executing in Ring 0 can execute any instruction that the CPU provides and can access all memory. Ring 3 has the fewest privileges. All the instructions are restricted to the set of instructions that are relatively safe. In practice, most operating systems actually only use Ring 0 and 3. OS2 and Zen are the notable exceptions that make use of Ring 1. Newer systems with virtualization extensions, either the Intel VTX extensions or the AMD V extensions, add an extra privilege level below Ring 0. This is colloquially sometimes referred to as Ring -1. And this mode enables instructions that allow multiple operating systems to share the same processor. These instructions help systems support hosting multiple virtual machines at the same time. Now, regardless of the number of modes available, whenever we wish to change modes for whatever reason, we have to perform something called a mode switch. And that occurs whenever the CPU switches into user mode, kernel mode, or hypervisor mode, or whenever an x86 CPU changes which protection ring is presently effective. Mode switches have the potential to be slow operations compared to other machine instructions depending upon the hardware. A notable example was the first generation of Intel Core 2 series processors, in which the mode switches into and out of hypervisor mode were quite slow. One situation in which a mode switch might occur is when something called an interrupt happens. And an interrupt is simply a situation in which the currently executing code is interrupted so that an event can be handled by the operating system. Interrupts can fall into two categories. We can have involuntary interrupts, which are external to running processes. These consist of things such as I/O interrupts, which are generated every time you press a key on the keyboard or perform any other I/O task. Clock interrupts, which are timer mechanisms that can be scheduled to go off at a particular time. And page faults, which have to do with the virtual memory subsystem. Interrupts can also be voluntary, in other words, created by a process that's running. System calls and exceptions, such as segfault or divide by zero actions, can result in interrupts as well. And the CPU provides hardware mechanisms for detecting when an interrupt is occurring and handling the interrupt. So in summary, multi-programming systems allow multiple applications to run simultaneously. Implementing multi-programming requires support from the hardware. In particular, we need CPU privileges, we need a clock, and we need some kind of interrupt handling mechanism. The CPUs used in multi-programming systems need to have at least 2 privilege modes. Intel x86 systems support 4 or 5 modes depending on the processor. Mode switches can be expensive in terms of performance, so we don't want to do them more than necessary. And interrupts enable hardware events to be delivered to applications, and they allow applications to yield control of the system while waiting for events or waiting for services.